Hey Stats, how's it going? Hope you guys are doing well. We are in our week after break. I had a dream last night that we went back to school May 1st. That's this Friday. I don't think that's happening. But I guess there's still a possibility we'll be going back in June according to Mr. Gagne, but we'll see. But I hope you guys are doing well. I hope you're staying safe and trying to keep yourself busy and not being completely bored. Some of you I know are your parents are making you stay home, and others are their parents are letting them, hang out with friends and stuff, and that's okay. We're all kind of in different situations right now, so it's tough. But yeah, we're gonna continue section 9.1. So we kind of did. I called it section 1 and okay. So I called it parts 1 and 2 of 9.1. We're going to continue into parts 3 and potentially 4, depending on how long this video is. I'm not going to try to give you more than an hour of total work in a week. It's hard for me to judge that. But your assignments this week are going to be to complete the notes again. It's a new set of notes, but same thing. Complete the notes, take a picture, upload to Google Classroom, and then there's one question from the book that you're going to be doing. Later in this video or in the next video, I'm going to be going over that homework question, so you might want to actually stay tuned in for that. So, as a review of what we talked about last week in the beginning of section 9.1 on sampling distributions, we talked about what it means, what statistical inference means, which is the process of making a conclusion just from some small sample. So we're taking a sample, we're drawing a conclusion about the entire population. Remember, a sample is just a subset of a population. We talked about the difference between parameters and statistics. A statistic is calculated from a sample, a parameter is calculated from a population, and the common number summaries we use are mean and proportion. We did some examples. We talked about sampling variability. Sampling variability is basically the idea that when you pick a sample from the population and then you pick another sample from that same population, they're probably not going to be the same exact thing, right? Because it's a sample is a random process. So if I have a population of 550 students at Herman High School and I pick 5 at random, and then I pick 5 at random again, there's going to be variability. They're probably not going to be the same. And that is the idea of sampling variability. So we looked at that through an activity where I had 200 chips. So the population size was 200. And then I would take samples of 20. The sample size was 20. And I knew in my population that half the chips were blue and the other half were green. And when I picked 20 chips from that bag, I calculated which percent were blue. I believe it was blue. And this is what we got in 25 different samples. So you can see the sampling variability and how it changes from sample to sample since it's a random selection. We looked how the dot plot looked for my selections. And that is where we stopped. Okay, so this is where we're going to continue. And these notes are on Google Classroom. You can print them if you have a printer. You can type them on the computer. Or you can just handwrite them. Okay, or on a regular piece of paper. You don't have to have a printer. So we're going to talk about a sampling distribution. And what is a sampling distribution? So, the sampling distribution of a statistic lists all possible values of a statistic and how frequently they will occur. Note each possible statistic, range, median, proportion of males, etc. has its own sampling distribution. So basically what this is, you look at a population, such as our 200 chips, you take a sample, you find some sort of statistic, whether it's range, median, what we found, was proportion of blue chips, right? So let's say we just keep going with that example. We're finding proportion of blue chips. But in a sampling distribution, it's when we take all possible samples. Now, you might think, okay, if you take 20 chips at a time as a random sample, there's a whole lot of possible different samples I can get. All right, so a sampling distribution shows all possible samples. And that is not what we did in our last activity. We did not take all possible samples. We just took 25 random samples. All right, so in a sampling distribution, you'll usually see that displayed as a dot plot or a histogram. And we're going to get into really what that looks like. So in the previous activity, where we took random samples of the chips, the class only took 25 different random samples, simple random samples of 20 chips. There are many possible simple random samples of size 20 from a population of size 200. If we took every one of those possible samples, calculated the value of p hat for each, and graphed all those p-values, then we'd have a sampling distribution. Okay, so that's if we took every one of the possible samples. Now, that would take us quite a long time. And you might be questioning, well, how many samples are there? If I pick 20 chips from a bag of 200, how many possible samples are there? And I'm going to tell you there's well over a trillion, well over a quadrillion. Okay? So we're not obviously going to do that, although computers can do it. So, next example says we used Fathom software, it's just a software program, statistical software program. We used Fathom software to simulate choosing 500 simple random samples of size n equals 20 from a population of 200 chips, 100 red, 100 blue. Same thing we did in our activity from last week, right? Except instead of taking 25 samples, they took 500. And they did that with a computer program. So then this figure on the left, figure 7.2, is a dot plot of the values of p hat. So that's this figure right here. You'll see the dot plot, the sample proportion of red chips from these 500 samples. Remember, we made a dot plot for our 25 SRSs? Well, they did it 500 times, not 25 times. They did it 500 times, and this is what they got. What does this dot plot look like? All right, well, I think there's going to be a question about that. So, A, is this the sampling distribution of p hat? The answer to that is no. This is just a simulation of 500 samples. It is not a sampling distribution because it doesn't show the values in all possible samples. So, I've said this numerous times already, a sampling distribution shows all possible samples. The statistic, whether we're finding mean, proportion, and all possible samples. Okay, so this is what I stated before, picking 20 chips from a population of 200 chips, just imagine the chips are labeled 1 to 200, and you pick 20 chips. So you pick 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, up to 20. Then you take the 20th chip out and put the 21st chip in. That's your second sample. You take the 21st chip out, put the 22nd chip in. That's your third sample. You keep going up to 100, right? But that's only replacing the last chip. So this is how many samples there actually are when you're picking 20 chips from a population of 200 chips. I don't even know how to say that number. I'm going to be real with you. Million, billion, trillion, quadrillion, something with a 5. Probably like an octillion, I'm going to guess. Alright, so this is not a sampling distribution. There's only 500 samples. This is how many samples exist. If we showed the dot plot with all of these instead of the 500, then it would be the sampling distribution. So question B, describe the distribution. Are there any obvious outliers? So looking at this, This is mostly bell-shaped. This seems to be an outlier. The center is around 0.5, which we would expect because in the population, half the chips are red, half the chips are green. I might have mixed up the colors, but it was at a 50-50 split. So the center is 0.5, right? The spread, everything's really centered around 0.5. It is spread out quite nicely, but like a normal distribution. It has the same spread as a regular normal distribution. So, to put that more formally, the shape is symmetric, unimodal, somewhat bell-shaped. The center is at about 0.5. The spread, okay, I gave the range of numbers. We're at about 0.25 to 0.75. The outliers, 0.15 stands out, right? So in that case, that was a sample where 15%, we picked 20 chips, 15% of them were green, right? So that's an outlier. We would expect it to be about 50-50. So the next question, C. Suppose your teacher prepares a bag with 200 chips and claims that half of them are red. A classmate takes a SRS of 20 chips. 17 of them are red. What would you conclude about your teacher's claim? So I'm saying you don't see ahead of time that there's 200 chips in the bag, half of them are red. But a student comes along, takes 20, 17 of them are red. Would you think from your one sample that the teacher's lying or the teacher's telling the truth? So here's what I wrote. I said, it's unlikely to obtain an SRS of 20 chips in which p hat equals 17 over 20, right? Because you got 17 of that color chip, so 17 divided by 20 is 0.85. That seems unlikely if it's a 50-50 split in the population. From a population of 200 chips, half of which are red. Oh, that's a continuation of the last sentence. Okay. In fact, a p hat of 0.85 or larger never occurred in our simulation of 500 samples. It seems doubtful that the bag contains half the chip, so it's probable, or it's possible, but not probable that that would happen. So I would think my teacher's probably lying, but I really don't know for sure, right? Unless I look at that entire population. But I only took a sample. So there's really no definite answer to this. It just seems doubtful. Because if we think the population is a 50-50 split, but we get 85% greens or reds, then it's probably not a 50-50 split, right? Especially when we look at those 500 samples that never even happened once. Actually, 0.15, which is just as likely as 0.85, happened 1 out of 500. Very unlikely. So that is the idea of a sampling distribution, where you take all possible samples. Now we are actually going to, by hand, make a sampling distribution. But it's not going to be a octillion possible samples. It's only going to be a couple. So here's our example. A population of 5 people and their score on the AP exam is shown below. So we have Adam, Betty, Carol, Daniel, Emily. All right. So we have Adam had a 3 on his test, Betty had a 4 on her test, Carol 2, Daniel 5, Emily 4. It's going to ask about gender later, so I just said who's male and female. So, part A. Suppose that a random sample of size 3 is chosen. So I am picking 3 of these 5 at random, but I'm going to list all possibilities. So it's really not random. I'm telling you what we're going to write out all the possible outcomes. So in a systematic order, I'm going to say Adam, Betty, and Carol, the first 3. That is my first possible sample when I pick 3 of these people. We're going to calculate, I think this is for later. Did it say to do this? Yeah, we're going to make this table. We're going to calculate 3 statistics. The mean, the median, and the proportion of, this is for later, so, of males. Alright, so this is, let me just write that in. I'm going to keep it as a fraction because it's going to be out of 3, right? 1/3, 2/3. We'd have to round if we change it to a percent or decimal. So to get the mean score, we take A, B, C, 3 plus 4 plus 2, divided by 3. 9 divided by 3 is 3. the median. So if you lined up 2, 3, 4 in order, 3 is in the middle, and P hat, that's a proportion of males. So we had Adam, Betty, Carol. So there's 1 out of 3 males. Why did I write 2 out of 6? Yeah, just 1 out of 3. Okay? So that's one sample. We're doing all possible samples. Just to keep this in order, I went A, B, D. So I took off C, and I put in the next name on the list. I already have the, I didn't show the work here just for the sake of time. Let's just do it one more time, though, for A, B, D. So how did I get 4 for mean? I took 3 plus 4 plus 5. So that would be 12. 12 divided by 3 is 4. So the mean is 4 from that particular sample. The median, we're going to line up in order from least to greatest. So 3, 4, 5. So the median is 4. P hat, proportion of males. Out of the 3 people selected here, we have A, B, D, 2 are male. Right? So there's 10 possible samples, and I wrote them all out here. So this is a sampling distribution. I took all possible samples of sample size 3 from the population. Much easier to work with than a sample distribution of like 1 million, right? This is just 10. So you will see here how X bar, which is the mean, ranges. It goes 3, 4, 11 thirds, 10 thirds, 3, 4. Now remember 11 thirds, just to put this in perspective for your own number sense, it's between 3 and 4. That's 3 and 2 thirds. And 10 thirds is 3 and 1 third. So that pops up numerous times. We have 13 thirds is actually the highest. That's 4 and 1 third. So you'll see how there's some variability. There's sampling variability for the mean. There's sampling variability for the median and for p hat, right? So this is our sampling distribution. So you can pause it, copy that down. So next part here, we're going to make a graph. Graph the sampling distribution for the sample mean score, sample median score, and the proportion of males. So we look at our table, make a graph for each of those statistics. First, we're going to look at mean. I made a histogram. So you can see here I have sample mean labeled on the x-axis, the count. So I have, if you go back to the table, how many people, how many times in a mean of 3 pop up? It popped up twice. Right? So if you look here, once here, once here. And you just keep going through. So 3 and 1 third popped up twice as well. 3 and 2 thirds popped up twice. Actually, I think that was 3 times. Yep, 3 times. So you can see how I have my x-axis labeled. I have my minimum, my max, and I just counted how many times these happen. Alright? Then I did the same thing for median and the same thing for p hat. So you can see this is somewhat bell-shaped. This right here is just, it's just 2 values, so this histogram doesn't show a whole lot. It's just really showing that there's a lot more 4s and 3s. And here, this is, I guess, somewhat bell-shaped as well, where 1 third occurring as the mode. Alright. Find the mean of the population and the mean of the sampling distribution. I feel like I have this worded differently in your notes. Okay, yeah, so I reworded it on the, I had already reworded it on the document that's on Google Classroom. So it says find the mean of the population, then find the mean of the sampling distribution of mean test scores. What? Okay, what is that saying? Find the mean of the population. So let's just start there, okay? So we're going to look at test scores. Find the mean test scores of the population. Our population is 5 test scores, right? That's everybody. We're going to add those 5, divide by 5. So it's pretty simple. 3 plus 4 plus 2 plus 5 plus 4 divided by 5. That's 3.6. That is the mean of the population. Okay? So it's the mean test score out of those 5 students. So the next thing right here, find the mean of the sampling distribution of mean test scores. So what this is really saying is when you look at your table here, we have mean test scores. This is the sampling distribution of the mean test scores. Just take these 10 numbers and find the average of those. Okay? Find the mean of those. So we're taking the mean of the means, right? And there's a reason for this, and you're going to see it. So I'm finding the mean of the sampling distribution of mean test scores. So I go through each of those 10. I add them together. I divide it by 10 because there's 10 numbers. And I get 3.6. That's the same thing I got for the population. No way. So that's interesting. That's saying when I take a sample, on average, I will get the same mean that I get for the population. So taking a sample and finding the mean is very much an accurate representation, most of the time, of the population. Okay, next part, basically the same thing, but we're doing it for p-hat, and we're doing it for median. So this is for P. Find the proportion of males in the population. Then, find the mean of the sampling distribution of the proportion of males. So, in the population, there's 5 people. 2 of them are male. So, P is 2 out of 5.4. Now we're going to take the mean of the p-hats in the sampling distribution. We're going to take this column, those 10 numbers, and average them. We add them together, divide by 10, and once again, we get 0.4. So, the population proportion, 0.4, is equal to the mean of p-hat in the sampling distribution, 0.4. So that means even if we took one sample, on average, we would expect the same proportion of males as we get in the whole population. You'll see I wrote these 2 little equations. That's what I just said. The population proportion is equal to the mean of all the p-hats when you take all possible samples. The mean of the population is equal to the mean of all the means when you take all possible samples. So this is giving us a lesson on sampling and that it can be accurate. On average, we will get a very accurate sample. When I say on average, remember there could still be variability as indicated in these graphs, right? We're just saying on average we'll get the same mean or proportion of males. So the next part, find the median of the population. Then find the mean of the sampling distribution of the median test scores. So we take these 5 numbers for the population. We put them in order. Take the middle number. That's 4. All right. Pretty basic there. Then we're going to take the mean of all of these as we have on the last 2. Add them all up. Divide by 10. We get 3.7. Not the same as 4. So it's not the same phenomenon that was happening with mean and proportion, right? So, on average, we won't get the same median. When we're sampling, the average sample won't have the same median as the population. So median is not as reliable when you're sampling. Okay, sampling is best to find mean and population, or proportion, sorry. when you're sampling, using a statistic that's accurate is obviously what you want to do. So you want to use mean and proportion, probably not median most of the time. Okay. Phew. That is part 1. But that leads basically to part 2. I guess part 3 and part 4 is how I put it. Instead of making a second video, I'm just going to continue. Okay? Because it's really based off of what we just did. Okay, yeah, so that leads nicely into variability and bias. So this will be real quick. A statistic used to estimate a parameter is unbiased if the mean of its sampling distribution is equal to the true value of the parameter being estimated. The two unbiased estimators we will be studying are means and proportions. So, as this just stated, the mean of its own sampling distribution is equal to the true value of the parameter being estimated. We saw that here, right? Means and proportions. The median is a bias estimator, not unbiased. All right? So unbiased means the statistic is doing a good job at modeling the population or the parameter. Bias means it's not doing a good job. So we're also going to look at variability. The variability, variability, standard deviation, range, it's spread. Okay? So the variability of a statistic is described by the spread of its sampling distribution. So when we look at the word bias, we're really concerned with the center of the sampling distribution, because we took the mean of the means, the means of the proportions, means of the medians. Mean is a measure of center. And we're looking at variability, we're talking about spread. So when we say there's high bias, we're saying the center of the sampling distribution is far from the center of its parameter. It's not a good predictor. Okay? When it's bias, basically, that was like the median. But unbiased would be the mean and proportion. So a quick example. This is a little abstract, but we have 3 graphs, and we have statistic A, B, and C. If the actual value of the population parameter is 5, which dot plot displays the estimator with low bias and low variability? Okay, so what is this really asking? Well, first of all, it's saying the actual value of, it doesn't say what statistic are we measuring. Are we measuring mean, median, range, proportion? It doesn't say, it's just saying 5. That is the correct amount for the population. So first of all, let's see. Which of these two have low bias? Bias is about the center of the sampling distribution. A low bias, opposite a high bias, the center of the sampling distribution would be close to the center of the parameter. So these two would be low bias because the center is at 5 for the statistic, just as it would be for the population. Right? So we're going to cross this one off. This one is high bias. These are each low bias. Okay, and which one has also low variability? Well, we've already narrowed it down to these two. Which one has the lower spread? Which one's not as spread out, but closer together, around the center? And that is statistic A. So that's low variability, high variability. So that's just statistic A. Oh, I wrote some stuff. Okay. Well, yeah, basically what I already summarized. So statistic A has low bias and low variability. So those are just two kind of key terms, bias and variability, that you'll be seeing. But the thing to understand is this is all just about sampling. All right? Which measures are good measures to use when we only have the sample to make a prediction about the population? The measures that are good to use that we've looked at so far out of the 3 are mean and proportion. Okay, and we looked at the reason why. Because on average, it will predict it correctly. Right? So that is it for this video. I'm going to make one more video where I kind of help you out with that homework question from the book, or I guide you through it. But remember, those notes, that is the first part of your formative. If you've been watching this video for a half hour, that's hopefully you've been taking notes as you go along. So it's done. Okay? So I'll see you next video. Bye.